All right, let's go ahead and do this one problem and then we'll talk about other stuff. So this question says, in what direction does the function f of xy equal to x squared plus 3xy minus 4y squared decrease most rapidly at the point 2 comma 1 comma 6? So I'll point out that if you're on a slope, I always imagine a hill, right? I'm on a hill. And if I want to find the direction that it's increasing most rapidly, I'm trying to go up the hill as steeply as possible. And if I'm trying to find the direction that's decreasing most rapidly, I'm going to turn around and go the opposite direction. Instead of going up as steeply as possible, I'm going to go down as steeply as possible. So really all I'm trying to do here is find the opposite direction that the gradient points in. That's all we're going to do. So we'll start off by saying that the gradient of f evaluated at the point 2 comma 1. I don't really need to throw in the 6 there because the 6 is the output value. That's going to give me the direction of most rapid increase. I'll say again, the gradient vector at a particular point always gives us the direction where we're increasing the most rapidly. So we're going to find this here. Let's see. The gradient just as a vector is the partial derivative. So we're going to get a 2x plus 3y for the partial with respect to x, and a 3x minus 8y for the partial with respect to y. So then we're going to plug in our point. We're going to say the gradient evaluated at 2 comma 1 is going to be 2 times 2 plus 3 times 1, comma 3 times 2 minus 8 times 1, which ends up being the vector 7 comma negative 2. Let me see right now. Is that better to see, hopefully? Okay. So then the answer to our question is that the direction of most rapid decrease is just going to be the negative of that. It's the negative of the gradient evaluated at 2 comma 1, which in this case, we're just going to literally multiply each thing by -1 and get -7 comma positive 2. At this point, we should think about whether we have. So I would say this points in the direction that I'm talking about. But if we wanted a uniform answer so that everyone had to give the same answer, we would normalize this vector or unitize it, divide it by its own magnitude. So we can say, or we can say the unit vector -7 comma 2 divided by its own magnitude, which is going to be 49 plus the square root of 49 plus 4. So we can say this is 1 over root 53 times the vector -7 comma 2. Has your instructor given you any kind of inclination, one way or the other, as how they want you to write direction vectors? It's okay if the answer is no. I'm really just curious. You're like, we don't know. Okay, that's fine. And so you definitely make sure you pay attention if that comes up so that you know which way you should be answering it. Let's go ahead and move on to talking about maximizing and minimizing functions. So I always hesitate to draw this next picture because I'm not good at drawing it. So I'm just going to show you the picture that I have right here, and you can all look at it. So there's 3 kinds of places that we're going to look for as far as like finding an extreme of a surface. So unlike functions back in 17a and 17b, where you find the max or minimum by just finding where the tangent line is horizontal or the slope is 0. Well, actually, that's the same. Actually, I'm kind of saying things aren't true. Kind of like back then, where we had maybe maxima that looked like this, or minima that looked like this, or even kind of what we would, inflection points where it might kind of like flatten out for a second. All those are places where the derivative of a function of one variable would be equal to 0. In a similar way, we're going to look at surfaces where maybe we have a maximum, like a downward opening paraboloid, or a minimum, like an upward opening paraboloid, which is the easiest one for me to draw. Or, okay, here we go. Hold on. I know I said I wasn't going to draw, but I'm trying to draw a saddle which like that. And all of these surfaces have a point where the tangent plane is essentially parallel to the xy plane, or you can think of it as being flat. Or another thing is the directional derivatives in both, well, actually in any direction are all zero. Because no matter what direction you're pointing in, you're not going up or down the slope, you're just going horizontal, parallel to the ground. So in this picture, and this is where my picture might fall apart, I'll try and make sure it doesn't. We have like a horizontal tangent plane. We're down here. We have a horizontal tangent plane. Or here, this is the hardest draw because it's above and below the surface at the same time. It's above the surface in the direction towards and away from you. It's below the surface in the direction that's left and right. So my picture probably, well, we'll see what we can get here. Yeah, maybe that's plausible. You could maybe pretend it looked okay, sure. But in each of these cases, all the directional derivatives are zero. But to find these tangent planes, essentially, to find the points where we have a tangent plane, you only have to check that both the derivative in the x direction and the derivative in the y direction are equal to zero. So we need the partial derivative in the x direction and the partial derivative in the y direction to be zero. And that's kind of the whole thing. So to find critical points for functions of two variables, we're going to find where both fx is equal to 0 and fy is equal to 0. Or another way of saying that would be saying that the gradient was equal to 0. So you might hear your instructor talk about finding where the gradient's 0. That's kind of a fancier way of saying it, but it's still true. So when we're trying to find critical points of a function of two variables or a surface, you're looking for the points where both the derivative in the x direction and the derivative in the y direction are both 0 at the same time. And we'll talk more about that as we go on here because sometimes you can trick yourself into thinking you have a critical point when you really don't. So let's look at some easy-ish examples here. Like I know I had another piece of paper here somewhere. Yes, sorry, I'm always looking for place here. So let's look at this example. So we want to, usually the words we use are find, we'll talk about classifying as well. Find and classify all relative extrema. Your instructor might call them local extrema. Meaning they're just bigger than or less than all the things near it, but maybe not everything everywhere. Of the function or for the function f of x comma y equal to x squared plus y squared minus 2x plus 4y plus 3. And so here's the typical process for doing this first part. We're finding the critical points or the critical points. So take your partial with respect to x, which is going to be 2x minus 2, and set it equal to 0. Similarly, take your partial with respect to y, which is 2y plus 4, and set it equal to 0. And then solve. Now, sometimes in this example, it's really straightforward. We're just going to get x equal to 1, and we're going to get y equal to negative 2. So we have one critical point. The critical point is the point 1 comma negative 2. And if you look, that critical point where x is 1 and y is negative 2 makes both of these partial derivatives equal to 0 at the same single point. X comma y equal to 1 comma negative 2. Cool. More interestingly, maybe, I don't know, we're going to classify this critical point. Is it a maximum? Is it a minimum? Is it a saddle point? here's how we test to see if that's true, which one it is. So we're going to find this thing called or we're going to use what's called the second partials test. So we're going to find this thing, which is typically labeled as capital D. So capital D, here's what it's equal to. It's the second partial with respect to x multiplied by the second partial with respect to y minus the mixed partial squared. So kind of like back in 17a, if yeah, it really is like the second derivative test. So I'll leave this to the side for just a second, and I'll remind you that, yeah, sure. So reminder, we did learn something called the second derivative test in 17a. I know it's been a while, but the second derivative test essentially said if you've got a critical point and your second derivative is positive, well, then you have to have a minimum or a maximum. Well, looking at my picture, what kind of thing do I have? You can say words, it's okay. A minimum. On the other hand, if your function has a critical point and the second derivative was negative, aka concave downward, then that point has to give you a maximum. And then if the second derivative was equal to 0, the test was inconclusive, which is why we didn't really like the test. But one of the reasons we talked about that test is so that we would be ready to understand how this test works in a similar-ish sort of way. So here's how this test is going to work. We're going to find D, and then one of technically 4 things is going to happen. Really, the 3 are the ones that matter. So if your D is negative, that's going to mean you're going to have a saddle. You know what? Let me actually write this down later so that there's a little more space. Let's just do this one, and I'll write it down in a minute. So we're going to calculate D here. So fxx is 2. fyy is also 2. And fxy is 0. All right. So our capital D is equal to 2 times 2 minus 0 squared, which is 4. If D is positive, and we'll write this down all in a minute, but if D is positive, which it is in this case, that means you either have a maximum or a minimum. So then you have to check one of your second derivatives. So my second derivative is fxx or fyy. Both of them happen to be, in this case, positive or negative. They're both positive. And we just said if the second derivative is positive, the function is concave up, which means we have a minimum. So D being positive means you have a max or a min. And then we check and say, oh, wait, one of my second derivatives is positive, which means we are concave up, which means we have a minimum at the point 1, negative 2. We'll write down kind of the rules in a second here. So that's the idea. I would like to show you what this looks like just so you can kind of really believe it. So let me 1 second here, Annika. So let me pin myself here 1 moment. Sorry. And also, let me give you the attendance form link. And by the way, I left the attendance form up there. When you have a second, you don't have to get up and fill it out right now, but do make sure you write your name on there before you leave today. So let's go ahead and graph this function. Well, come on, cursor, get over there. Where's my graphing stuff? There you are. There we go. Cool. I always click on this one. I need to, no, that's right. Okay, fine. Sorry, I thought this was a bad link that I was using. So if we graph z equal to, well, I'll point out x squared plus y squared should tip us off that we probably have an upward opening paraboloid. So if x squared plus y squared plus or minus 2x plus 4y plus 3. Yeah, it's a paraboloid. And if you can clearly see that if you have a critical point here, it's definitely going to be a minimum, right? No bones about it. We can also plot it if you really wanted to, though. That point was x is 1, y is -2, and I guess I have to plug it into the function to find the z value. Let's see. 1 plus 4 is 5, -2 is 3, -8 is -5, plus 3 is -2. There it is. You can kind of see it at the very bottom there, right? Oh, yeah, look, there it is. Our minimum right there at the very bottom of my paraboloid. So let's go ahead and write down the criteria here. So to classify critical points of functions of two variables, we first calculate d, which is equal to fxx times fyy minus fxy squared. I'll point out that the last example we just did wasn't particularly interesting because we didn't actually have to plug in our critical point because there weren't any x's or y's left over when we took the second derivatives. That won't always be true. A lot of the time there'll actually be a value of x and y, and we'll have to plug in our critical point. So calculate d, and then plug in each, because there could be more than one, critical point. Let's call them x naught comma y naught. So then four different things can happen. First possibility, if d evaluated at x naught comma y naught is negative, then we have a saddle. At x naught y naught. The second thing that can happen is if d is positive, then you have to do a little bit more work. You have a maximum or a minimum. And that's when you look at one of the second derivatives. So we do more work. If either of your second derivatives is positive, so if fxx or fyy is positive, that means we have concave up, so we have a minimum. I would highly recommend when you think about this part to think about it in terms of the concavity. Because I always used to mess it up like, oh, it's positive. That means no, positive does not mean the maximum. Positive means concave up, which means a minimum. So we have a minimum. And on the other hand, if either one of those is negative, then we have concave down, which means we have a maximum. And then lastly, somewhat like the second derivative test back in 17a, if this capital D thing happens to be equal to 0, then the test is inconclusive. We don't know. So those are the things that can happen when you find and classify critical points. Let's see here. 1 second here. The questions about that before we do some more examples. We'll do one more. So let's look at another relatively easy-ish example before we move on to some harder examples. In fact, I might have you all do this one. So yeah, so why don't you try the following? So your function f of xy is going to be 2x squared minus y squared plus 4x plus 6y plus 1. I want you to find and classify the critical points. So find the critical points first. And again, you're going to do that by taking each partial derivative, fx and fy, and setting them equal to 0. So go ahead and do that. I think you're only going to get one critical point here. So go ahead and find your one critical point and then see if you can classify it. If we look at our partial derivatives, fx is equal to 4x plus 4, fy is equal to negative 2y plus 6. We set each of those equal to 0. We're going to get x equal to negative 1. We're going to get y equal to positive 3. So we get the single critical point, negative 1 comma 3. Now we're going to calculate d. D is equal to, people often skip writing out this part. You can go either way. I like writing it out to remind myself of what I'm doing. Fxx here is just 4. Fyy here is negative 2. And fxy again is 0. This is equal to negative 8, which is negative. So that means we have a saddle at negative 1 comma 3. Something people often ask is, if you have a max or a min, how do you know you don't have to test like both second derivatives? Let me ask you all a question. I don't want to say this the right way. There's something I want to say. Oh yeah. So let me point out. If this quantity here, you probably don't need to write this down, but you surely can if you want to. So if this quantity is positive, is it possible for fxx and fyy to have different signs? Could fxx be positive and fyy be negative? Well, what if they were? A positive times a negative is negative. And if you subtract something positive, because it's squared, it has to be positive, it's going to be more negative. So the answer is no. These two things cannot have opposite signs if this whole thing is positive, which is why you only have to test one of them, right? If this whole thing is positive, we know, great, both fxx and fyy have the same sign, either both positive or both negative, so we only have to check one of them. So be assured that when you're testing to see if the max or min, you can either just look at fxx or just look at fyy. You do not need to look at both. Let's look at some more examples. They do get more interesting. These first two I think are kind of boring. Let's do some more exciting problems here. So let's say we have something like 4 f of x comma y is equal to x to the 4th plus y to the 4th minus 4xy plus 2. Same spiel, right? Find and classify. Critical points. We do call them critical points, not critical values, because they are literally a point, right? It's an XY pair, not just a single value of X or Y. So let's go ahead and find them. So fx is going to be 4x cubed minus 4y. Fy is going to be 4y cubed minus 4x. And these two equations don't immediately lend themselves to just finding an x and a y value. So in a problem like this, you have to kind of do more work. Typically, finding one thing instead, like solving for one variable and then substituting that into the other equation. So I would point out a couple things. The first equation, actually both of these equations you can divide by 4. So this you can think of as being just x cubed minus y equal to 0. This one being y cubed minus x equal to 0. And I'll say that at the end. So I'm going to solve one of these for y, sure. So I'm going to get x cubed equal to y, and then I'm going to plug in x cubed to the other equation for y. So I'm going to have x cubed minus x equal to 0, or x to the 9th minus x equal to 0. Factor out an x, if x to the 8th minus 1. So either I get x equal to 0 or x equal to 1 or negative 1. We're not done finding our critical points because we've only found half of each critical point. So if x is 0, y is equal to x cubed, so y is going to be 0. If x equal to 0, we get y equal to 0. We get the point 0, 0. If x equals 1, y is equal to x cubed, so y is equal to 1. And if x equals negative 1, then we get y equal to negative 1. something I want to point out because it comes up more often than you might imagine. These two partial derivatives are what we would call symmetric. What that means is if you were to interchange x and y, each equation would still be the same as each other, or you still have the same set of two equations, right? If I interchange x and y here, I get 4y cubed minus 4x. If I interchange x and y here, I get 4x cubed minus 4y. When that's true, which again, you think this is a special case, but it really happens relatively often. When that's true, it means all of your critical points are either going to be critical points where x and y are the same, like all the ones we have here, or if you get ones where they're different, then the inverse or the flip also has to be a critical point. So like if 2, 8 had been a critical point, 8, 2 would also have to be a critical point. They always come in pairs like that. So just something to think about or be aware of as you move forward in your critical point finding career. All right, so now we have to classify all three of these. So we're going to find our capital D. So capital D is going to be fxx, which is going to be 12x squared, times fyy, which is 12y squared, minus fxy, which is negative 4 squared. I can say without reservation, you almost never want to simplify this. It is almost always best left unsimplified because you're going to plug in some points. Let's see what happens. So if we plug in 0, 0, d of 0, 0 is going to equal 0 times 0 minus 16, which is negative 16. And if it's negative, that means we have is a what? It's a saddle. On the other hand, let's plug in 1, 1. So d of 1 comma 1 is going to be 12 times 1 squared. So 12 times 12 minus 16. I don't care what the number actually is. 12 times 12 is much bigger than 16. So 12 times 12 minus 16 is certainly positive. This is one of the reasons we don't want to simplify. If I don't multiply this out and make it like 144 x squared y squared, I can still kind of read where my second partials are. I would point out that that is our fxx value right there. So we can see, oh, this is positive. I know it's a max or a min. I also know that fxx is positive, which means we're concave up, which means we have a minimum. Similarly, if we plug in negative 1 and negative 1, we're going to get d of negative 1 comma negative 1, which is going to be still positive 12 times positive 12 minus 16, which is still positive, and our fxx is still positive, which means we're still concave up, which means I should have really said we have a minimum at 1 comma 1, and I should have said that here too. We have a minimum at negative 1 negative. I'm not on purpose, but just kind of leaving out the word local or relative, right? These are all local minima or maxima, or you don't really call a saddle a local saddle, like it's just a saddle. Yeah. This is a surface that has one saddle and two minima. I think it's worth looking at because I'm not gonna lie. I'm just a little bit jealous of all of you in that you get to learn three-dimensional math in a world where there are three-dimensional graphing tools readily available to use all the time. I remember when I was learning this stuff way back when, like they had just come out with like the TI 90-something calculator, and there was one kid in my school that had it, and you had to like read this book essentially to learn how to program it to do the thing. It was still cool, but you all are very lucky by comparison to have all these wonderful tools. So point out I'm a little bit jealous, but it also makes my job more fun to show you these cool things. So here's what this surface looks like. I don't really need the +2, but it kind of looks like a cartoon character pair of pants where they don't really have feet, right? And I will say, although excuse the language, it's not really bad. A saddle also looks like the crotch in a pair of pants. Like really like you got the legs going over this way and the other part going up this way, right? It's the same kind of deal. And that's exactly what we have here. We have a saddle right in the middle there, and we have two minima where your legs got amputated. That's what's going on there. Two minima, one saddle. Cool. All right, let's look at least one more because yeah, there's some other interesting things that happen here. Question, yeah.
So would we at least test like 0, 0, 1, 1, for like for most of these problems?
So every time we're going to get different critical points. So not necessarily, no. But whatever our critical points end up being, those are the things we're going to test in this capital D. By the way, this capital D is the reason it's called that is it's actually the determinant of a 2x2 matrix of second partial derivatives, which you will be learning about, not that particular, but you'll definitely be learning about finding the determinant of 2x2 matrices before the end of the quarter. So it's not that far off, and it's not that terrible to do. Let's look at least one more example here. Yeah, I like this one here. Oh, where'd you go? I don't remember exactly how challenging the problems get in this particular section, but it's good to have a little bit more familiarity with dealing with harder functions. So let's say we want to do the same sort of thing for, what is this, number 5? Yeah, number 5. We want to find and classify all relative extrema of the function f of x comma y equal to 3x cubed plus xy squared minus 9x squared minus y squared. And whether or not we like this, the process is always the same first step. You're always going to start by taking the two partial derivatives, fx and fy. So let's do that. Fx is, let's see, it's 9x squared plus 1 times y squared minus 18x, and that's it. Fy is equal to, let's see, 2xy minus 2y. And we're going to set each of those equal to 0. Now, a good rule of thumb is to try to deal with the one that looks like it's easier to deal with, like the one that looks less terrible. In my opinion, that's certainly the Fy here. Fy has less going on, it doesn't have any squares, and I can factor out a 2y. So if I deal with Fy here, factoring out a 2y, I've got 2y times x minus 1 equal to 0. So I either get y equal to 0 or x equal to 1. I want to be extra super duper clear about this next thing. 1 comma 0 is not a critical point. X is 1 or y is 0 makes this second partial derivative equal to 0. It does not make this first partial derivative equal to 0. If you plug in 1 for x and 0 for y, you're going to get 9 plus 0 minus 18, which is negative 9, which is not 0. So I just want to be clear because lots of people make this mistake. They think, oh, I get an x and a y from this. It's a critical point. But you have to have a critical point where both partial derivatives are both equal to 0 when you plug in the x and y value. So what that does mean, though, is that x equal to 1 makes this equal to 0, right? Because if x is 1, you get 2y minus 2y. So then if we plug in x equal to 1 over here, we can find the y value we need for this one to also end up being 0. So we're going to plug in x equal to 1 and get 9 times 1 squared plus y squared minus 18 times 1 equal to 0. So this ends up being y squared minus 9 equals 0, which we could factor or bring the 9 over, but I think you all can see we're going to get y equal to plus or minus 3. So that means for x equal to 1, there's two different corresponding y values that give us critical points. So our two critical points so far are 1 comma 3 and 1 comma negative 3. I'll point out that if we plug in 1 for x, doesn't really matter what you plug in for y in the second partial. 2 times 1 times 3 minus 2 times 3 is going to be 0. And in this first partial derivative, if you plug in 1 for x and 3 for y, you get 9 plus 9 minus 18. Yeah, that equals 0. So this critical point and this critical point make both partial derivatives equal to 0 at the same point on the surface. let's find the other critical points because we still have to also use, so we use this, now we're going to use this. So we're going to plug in y equal to 0 up here. We do that, we're going to get 9x squared plus 0 minus 18x equals 0. Here we're going to factor out because we can. So basically you're solving these equations in whatever way you can. Factoring when you can, solving when you can, doing whatever you can when you can. Factor out a 9x, I'm left with an x minus 2 equal to 0. So I have either x equal to 0 or x equal to 2. So the other two critical points I'm going to get are going to be x is 0 and y is 0. And x is 2 and y is 0. So I have 4 critical points. And now we're going to test each of them. So let's go ahead and find our capital D. The capital D is fxx times fyy minus fxy squared, which is going to be, let's see, fxx is going to be 18x minus 18. Fyy is going to be 2x minus 2. And fxy is going to be 2y. So there's my capital D. Yeah, I guess I'll do this. So I usually just kind of like to do something, but my friend, my coworker Grant, likes to make a little table when he does this. So here's kind of the table that he likes to make. He likes to say, okay, here's my critical point. Do I have enough room? Maybe. We'll find out here. Here's what D is equal to. I should have just written this there. Oh, well, sorry. 18x minus 18 times 2x minus 2 minus 2y quantity squared. And then we're going to leave ourselves some space for the sign of the second partial if we need it. And then finally, the conclusion. Okay, so let's start with, it doesn't really matter where we start. Let's start with 0, 0. I will point out more strenuously here, really, really not in our interest to multiply out 18x minus 18 times 2x minus 2. It's not going to help us do anything. If I plug in 0, 0, I'm going to get negative 18 times negative 2 minus 0 squared. I don't really care what it's equal to. I just care whether it's positive or negative. In this case, it is positive. So that means we have a maximum or minimum. So we do care about the fact that the second derivative is negative, meaning we're concave down, meaning we have a maximum at 0, 0. We're going to do the same thing for the rest of them. Plug in the critical point 2, 0. Well, now we're going to get 18 times 2 is 36 minus 18 is positive 18. And 2 times 2 is 4 minus 2 is positive 2. Still plugging in 0 for y, so we're getting that. And 18 times 2 is also equal to a positive number. They both end up being positive 36. Again, not that we really care. So again, since my D is positive, we know we have to see whether it's a max or a minimum, right? So if your D is positive, that really means you have to do more work. It's kind of like back in the day when we had limits that were 0 over 0. And yeah, that was an indeterminate form, but what it really meant for us is we had to do more work or more inspection. So here, the sign of fxx is positive. All right, it's again a good reason not to multiply this out. So I can still see that, oh yeah, there's my fxx right there. So fxx is positive, meaning we are concave up, meaning we have a minimum at 2, 0. Now for the other two, I plug in 1, 3. I'm going to get 18 minus 18 is 0. And really at that point, I don't care what I get over here. Because 0 times anything is 0. So 0 minus 2 times 3 is 6 squared. 0 minus 36 is certainly negative. I don't really care about the sign of the second derivative. Also, it doesn't have a sign actually because 0 and 0 is neither positive nor negative, but we don't really care. But since this is negative, we know that we have a saddle at 1, 3. And you can probably see we're going to do the same thing for 1, negative 3. Because again, if x is 1, we get 0 for that first part there. If y is negative 3, we get negative 6 squared, which is still 0 minus 36, which is negative. The sign doesn't matter here, and we get another saddle at 1 comma negative 3. Okay. Give you one more example, and then we'll call it a day. I like this example. So let's say we have something kind of not exciting. F of x comma y equal to x squared times y to the 4th. Do the usual work. Fx is 2x times y to the 4th. Fy is x squared times 4y cubed. And if we set these equal to 0, well, the only way to multiply to 0 is if one of the things is 0. So either, interesting. I feel like this, I think I'm looking at this solution here, but I think the solution is actually missing a little bit. So yeah. So we have a lot of critical points here. Let me show you what I mean. So in this first equation, if 2x times y to the 4th is equal to 0, you're either going to get x equal to 0 or y equal to 0. And certainly 0, 0 is a critical point in this problem. Because you plug in 0 for x here and 0 for y, right? 0 for both of them is 0. But I'll also point out that if x is 0 in this equation, well, that means y could be anything and it would still work. So actually, we have an infinite number of critical points. So my critical points are 0 comma anything and anything comma 0. Or a little bit more specific way of writing it would be 0 comma y, where y is any real number, including 0, and x comma 0, where x is also any real number. So in other words, the entire xy axis is all critical points. Here's the bummer. We can't classify any of them. Because if you look at the second partials here, fxx times fyy minus fxy squared is equal to, let's see, fxx is going to be 2 times y to the 4th. Fyy is going to be 12y squared times x squared. And then fxy is going to be 2x times 4y cubed, which is 8xy cubed. And if you plug in 0 for either y or x, everything's going to be 0, right? If y is 0, well, that's 0 and that's 0, so it's 0. If x is 0, that's 0, that's 0, so it's 0. So no matter what you do, d with any critical point plugged in is going to be 0, which means it's inconclusive. However, we can be, or I should say, most of the time when these are inconclusive, you can look at the original function and just kind of reason out whether it's a max or min, usually whether it's a max or min, it's usually not a saddle. So I'll point out, if you plug in 0 for x or 0 for y, f of 0 comma x in the original function is going to be 0, as is f of, 0 comma y, apologies, that's terrible. Or f of x comma 0, right? If you plug in the 0 for x, you get 0. If you plug in 0 for y, you get 0. Cool. If you plug in any other not critical point where x isn't 0 and y isn't 0, and you square x and you do y to the 4th and multiply them together, is the overall result going to end up being positive or negative? It's going to have to be positive, which means the smallest value this function can have is an output of 0, which means every one of these infinite critical points is a minimum. So every critical point is a minimum. It's actually an absolute minimum because it's smaller than every other possible value the function have. I do think this one looks kind of neat, so I'm going to show it to you, and then I'll let you, yeah. Well, I was like, oh, we're gonna be done. We're not gonna be done early. It's 1:58. Sorry, I feel like I made it sound like we were gonna be done early a minute ago, but that was a big lie. So let me just show you this last function here, and then you can be done at the usual time. So let's see here. This one's kind of cool looking. So let's see if we graph it here. It's z equal to x squared times y to the fourth. And look, every point on the axis is a straight up minimum, and then it just gets bigger and bigger and bigger as you move away from the axes. Kind of cool. I mean, as far as math goes. All right. That's all we got. Have a lovely weekend. I'll see you on Monday. Make sure you write your name on the sign-in sheet if you didn't already. And I have office hours over in C class as usual. And you'll have a midterm a week from this coming Monday, right? Okay. I do have, I haven't written it yet, but I do have a practice exam to write for you all, which I'll definitely give you before Friday of next week. Yeah, have a lovely day.